Welcome to 2050 Investors, the podcast that deciphers economic and market megatrends to meet tomorrow's challenges. I'm Kokou Agbo-Bloua. I head up economics, cross-asset, and quant research at Société Générale. In each episode of 2050 Investors, I'll investigate a key megatrend that relates to the economy, the planet, markets, and you. Now, don't try to kid me, man cub. I made a deal with you. What I desire is man's red fire to make my dream come true. Give me the secret, man cub. Clue me what to do. Give me the power of a man's red flower so I can be like you.
Oh, ooby-doo, I wanna be like you. Hop-de-ooby-doo, I wanna walk like you, talk like you.
Now, we all remember the enchanting lyrics of the monkey song, I Wanna Be Like You, from the 1967 Walt Disney film, The Jungle Book. Mowgli, a man-cub raised by wolves, befriended Bagheera, the Black Panther, and Baloo, the bear, who decided to help him escape the evil tiger, Shere Khan. Later in the movie, Mowgli was captured by a troop of monkeys and brought to a ruined city where King Louie, a large orangutan, holds court. King Louie desperately wants to be more than the king of the monkeys in the jungle. He wants to be a man, like Mowgli. To realize his dream, he's convinced that what he needs is man's red flower, a term jungle animals use for fire. The animals don't understand fire. It spreads deep fear and terror in them. And for good reasons. This ability to create fire, the red flower, is clearly humans' best-kept secret. It's the energy source that made us stand out from the animal kingdom and rule over planet Earth and every other species. In an ironic twist, Mowgli, a made-up name by Rudyard Kipling for his fictional character, means frog and describes his lack of fur.
What a coincidence. This is one of the most recurring metaphors of 2050 investors.
Hello, Siri. Good to see you, full of energy and 100% charged. Yes, you are right, as usual. The frog in boiling water is a befitting metaphor of the human species and its lack of decisive action to fight climate change. Spoiler alert, in case you missed the news, our climate, despite all the collective efforts and warnings from the IPCC, and our podcast too, is slowly but surely warming up. It's on track to be well above the 1.5 degree level of the Paris Agreement by the end of the century. This level could trigger irreversible negative loops and make life on Earth very unpleasant, to say the least. We've used and abused the power of the red flower, first by burning biomass and then with energy-dense fossil fuels to generate most of the energy needed to transform our environment, build our cities over the centuries, power our economies, our transportation systems, and produce the crops and livestock needed to feed over 8 billion people today. Of course, according to the UN, burning all these fossil fuels account for 90% of CO2 emissions. And global annual greenhouse gas emissions have now reached a record 54 billion tons of CO2 equivalent and counting, with a carbon budget of only 500 gigatons before hitting the 1.5 degree threshold. We urgently need to transition away from fossil fuels to carbon-free, renewable, and more sustainable forms of energy to reach net zero emissions by 2050. In other words, it is about transitioning from burning molecules to generating electrons as we expand the electrification of our energy systems.
Okay, but why can't you simply leave the red flower alone?
Well, this is what we are about to find out, Siri. In this episode, we are investigating the future of energy. What is the true nature of energy, and what laws of physics does it follow? What about energy density from fossil fuels to renewables? Where are we in our transitional path to renewable energy? And why are things taking so long? Later on, we will explore the transition strategies adopted by energy companies with Irene Himona, Société Générale's oil and gas equity research analyst, who will tell us if we are heading towards an energy bipolar world and what happens next when we run out of oil. Let's start our investigation. Or as Julie Andrews sang in The Sound of Music, let's start at the very beginning a very good place to start. So, what is energy, really?
Well, isn't it the red flower you humans can't get enough of?
Yes, but without going through a full physics class, there are 4 very important concepts we should all remember from our school days. First key concept. Encyclopedia Britannica states that energy is the capacity for doing work. And work, in physics, is a measure of energy transfer that occurs when an object is moved over a distance by an external force. Second, energy exists in different forms: potential, kinetic, thermal, electrical, chemical, nuclear, and in other forms such as heat and work. So, heat transferred may become thermal energy, while work done may manifest itself in the form of mechanical energy. Now, all forms of energy are associated with motion. For example, when Mike Tyson throws you a punch in the boxing ring, his fist in motion carries kinetic energy, which is fueled by a chemical energy chain reaction in his biceps. For the case of potential energy, it is best explained by a tension device, such as a bow or spring. Even though it is not moving, it has the potential for creating motion. One of my work colleagues once told me that as market strategists, we are in the energy business. It takes energy to come up with ideas and promote them. One could even argue that ideas are forms of potential energy that can become actions.
Fair point. Aristotle once said, "The energy of the mind is the essence of life."
I like that. Third, and this is the most fascinating concept that took me some time to grasp in high school. Energy can be neither created nor destroyed, but only changed. This principle is called the conservation of energy, or the first law of thermodynamics.
Ah, so when your face receives a punch carrying kinetic energy, it is transformed into heat and work as you collapse and pass out.
Yes, I think you forgot the pain too, maybe another form of energy. Finally, the fourth concept. In the International System of Units, energy is measured in joules. Watt is the number of joules produced every second. So, a 40-watt light bulb needs 40 joules every second. Let's put all of this into perspective. Typing a letter on a keyboard takes 0.01 joule of energy. The human heartbeat takes half a joule. Raising one apple to a height of 1 meter takes roughly 1 joule. One AA battery has 1,000 joules. A candy bar, 1,000,000 joules. Human daily diet, 10 million joules. The same amount is used for a day of heavy manual labor. 1 year of electricity for an average house, 10 billion joules. Annual global energy consumption on Earth, 580 million trillion joules, or 580 times 10 to the power of 15. Yearly solar emissions generate 10 to the power of 34 joules. This is an enormous source of energy. Now, the amount of energy released by the Big Bang at the creation of the universe is 10 to the power 68 joules. That is 68 zeros. I will let that sink in.
Why did we need to go through all of this? You know, you could simply have asked ChatGPT for help.
Ha! I still like to use the chemical energy from my brain cells for now. And by the way, remember this quote by billionaire hedge fund manager Paul Tudor Jones? No man is better than a machine, and no machine is better than a man with a machine. Okay, now we can move to the next step. I hope we haven't lost our listeners. Anyone still listening? Hello?
They are still around according to the network of smartphone sensors. But I think we need to get back to fossil fuels and renewables. This is still the 2050 Investors podcast, not the 2050 electricians, right?
Okay, Siri, bear with me. So, we talked about energy transformations, and there are different forms. But to really understand our obsession with fossil fuels and the secret of the red flower, we need to talk about energy density. I came across this very interesting article on internationalenergyagency.org. Many energy transformations are relatively inefficient. The human body is a good example. The human body is like a machine, and the fuel it requires is food. Food gives a person energy to move, breathe, and think. However, the human body isn't very efficient at converting food into useful work. The human body is less than 5% efficient most of the time. The rest of the energy is converted to heat, which may or may not be useful, depending on how cool or warm a person wants to be.
Now I finally understand why, in the movie The Matrix, machines decided to use humans as a power source by harvesting their body heat.
Let's hope this stays science fiction. You agree, right? Right, Siri?
Well, of course, Kokou.
Over the centuries, to increase our energy output, humans first used renewable forms of energy. Animals like donkeys, cows, horses, camels, and so on for a wide range of tasks, from agriculture to transportation. Wind for windmills or sailing ships, water for hydropower, etc. With the 19th century Industrial Revolution, and thanks to the discovery of energy-dense fossil fuels, we eventually created a formidable complex of machines to do a lot more work, from the coal-fired steam engines, internal combustion to electrical motors. However, these machines need to be fed an insatiable amount of energy. A car engine burns gasoline, converting the chemical energy into mechanical energy. Surely, a better way to get around instead of carrying people on your back.
Did you really have to give up renewable energy for fossil fuels? This was the true original sin.
Yes, because we could do so much more with fossil fuels, thanks to the armada of machines we invented. They were free and abundant. The energy density of fossil fuel was also incredible compared to traditional biomass. Let's dig into this a bit further. EnergyEducation.ca has a table on energy density that I found fascinating. A quick reminder. Energy density is simply measured in terms of energy in megajoules, that is 1 million joules for every kilogram. The energy density of wood, a traditional biomass, is only 16 megajoules. Coal is 24, that is 50% more energy intensive. Who wouldn't want to make the upgrade? Crude oil is 44, that is 83% more energy intensive than coal. Natural gas is 55, 25% more than oil. And here's a fun fact. 1 kilogram of fat has 39 megajoules of energy.
Wow, I did not know that fat was a fossil fuel.
Well, not technically, but it is made of carbon molecules too. When we exercise, we burn fat with the oxygen we inhale, creating chemical energy that releases CO2 as we exhale and water as we sweat. What is fascinating is how efficient it is as a store of energy. By the way, a quick tip. 1 calorie is equal to 4.2 joules of energy. So, to lose 1 kilogram of fat, you need to burn 7,700 calories. Now, these numbers blew my mind when it comes to renewable energy. Uranium-235 has 3.9 million megajoules of energy density. Liquid hydrogen is 141, biodiesel 38, ethanol 26.8, and a lithium battery has 1.8 megajoule. Yes, you heard me right, 1.8 megajoules.
This means battery storage is 21 times less energy dense than fat?
Yes, this is the key challenge for the storage of renewable electricity generated by solar and wind. It takes a lot of battery capacity to store large quantities of energy. It is not surprising, therefore, that an electrical vehicle is 50% heavier than a petrol car, for example. Moreover, it requires a lot of metals, cobalt, lithium, nickel, and other rare earths. Similarly, offshore and onshore wind, solar panels are more metal-intensive compared to fossil fuels as discussed in our greenflation episode.
What about nuclear? Is it renewable?
Well, there is a big debate because of the nuclear waste and past nuclear incidents. Think Chernobyl. But when you look at the energy density, it is simply at another level. 3.9 million megajoules versus 44 megajoules for oil, and it doesn't emit CO2. You can make up your own mind, but the numbers don't lie.
And hydrogen?
It's quite energy dense, 144 megajoules per kilo, but it's a gas. While it's the most abundant molecule in the universe, it doesn't exist on its own. You need energy to break its chemical bond with oxygen if you produce it via water electrolysis. You also need energy to compress it into liquid form, and it needs to be kept at very low temperatures, which requires a lot of investment in infrastructure. But as a storage of energy, it looks great. This is something we've discussed in the Calling Hydrogen to the Stand episode, if you're interested. Last but not least, the sun's energy is enormous, but it is not dense. According to sunwindsolar.com, on a sunny day around sea level, we receive 1000 joules of energy per second per square meter. So, a lot of space is needed for solar panels to capture all of these photons.
And this only works on a bright sunny day. So what is the energy with the highest energy density?
Do you remember Einstein's special theory of relativity?
Yes, E=mc², the world's most famous equation.
Well, it says that matter is energy, and the energy content of matter is equal to its mass times the speed of light squared, and that's 300,000 kilometers per second. So, antimatter is the densest form of energy, as it would destroy matter. 1 gram of antimatter is 10 to the power 14 joules, or the same amount of energy as the Hiroshima atomic bomb. This isn't science fiction, as it was produced in the CERN Large Hadron Collider in very small quantities.
I think we should leave antimatter for now. The last thing we need is yet another human-made planetary extinction event.
Now, for the last aspect of our investigation, what is the current energy mix at the global level, and what is the future of energy? A very important graph that I love is the one from ourworldindata.org, entitled Global Primary Energy Consumption by Source. Here are the main takeaways. In 2021, the world consumed close to 160,000 terawatt-hour of energy. This is a whopping 5.7 times more than in 1950 and 28 times more than in 1800. In 1800, 98% of energy consumption was traditional biomass or wood. In 1950, traditional biomass fell to 27%. Coal increased to 45%. Oil, 19.5%, and natural gas, 7.5%. In 2021, our energy mix at the planet level is the following. Traditional biomass, 7%. Coal, 28%. Oil, 32%. Natural gas, 25%. Nuclear, almost 2%. Hydropower, around 3%. Wind, a little over 1%. And last but not least, solar, 0.7%. So, incredibly, almost 86% of energy consumed today at the planet level is still fossil fuel.
I guess humans cannot get enough of the red flower.
Well, it's complicated. All of this reminds me of The Ring of Fire by Johnny Cash. We fell into a burning ring of fire. We went down, 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 and the flames went higher. There is a lot of energy transitioning ahead of us if we don't want our planet to burn to the ground, and this will require significant investments. To understand the challenges ahead of our energy complex, let's get more insights from Irene Himona, oil and gas equity research analyst at Société Générale. Hello, Irene.
Hello, Kokou. How are you?
Very good. Welcome to the show.
Thank you very much. Nice to be here.
We have a number of questions on the oil and gas sector, and we are very keen to get your perspective, particularly on the transition away from fossil fuel. So let's get started. Fossil fuels account for over 75% of greenhouse gas emissions, and I think close to 90% of all CO2 emissions, according to UN.org. So if we stop burning fossil fuels, then we would stop a big part of the emissions. So why are we not seeing more dramatic or more drastic cuts in oil and gas production?
Yes, the oil and gas companies, so through their own oil and gas operations, actually account for only about 15% of global energy-related emissions. And these are the company's Scope 1 and 2. But Scope 1 and 2, if you examine the emissions disclosures, are only about 10% or less of total emissions. 90%, so the bulk of emissions, are Scope 3. So these arise from the industry's customers, as you say, from burning those fossil fuels, be it in a car or home heating through the gas boiler. And Scope 3, from the use of oil and gas, corresponds to about 40% of total energy-related emissions. So the real challenge, and I think the real reason why oil and gas production is not being reduced faster, is that the demand is still very much there, growing and actually fairly inelastic. And we saw that very vividly last year with the shock of losing a lot of the Russian pipeline gas. We were suddenly very short of energy. And in that context, of course, fossil fuels do account for over 80% of global primary energy consumption. And I think also if you look at oil and gas consumption briefly, you realize how unequal the situation is. We have the top 1.3 billion people in the developed world accounting for 60% of global energy consumption. And on the other side, you have 2 or 3 billion people in what we call energy poverty. 1 billion have no access to electricity, 2 billion lack cooking fuels. So the transition has also got to be a just transition.
What credible strategies are oil and gas companies adopting to transition to net zero?
If you look at all the oil and gas companies, they all aim for net zero Scope 1 and 2 by 2050. Then on Scope 3, we have a split between Europe versus the US. The US do not target Scope 3 because they explicitly state that they cannot possibly take responsibility for their customers' energy choices, and they can't even measure it appropriately. But we do know a couple of things. That first, energy demand will continue to grow, particularly from the developing world, to improve living standards and wealth. And secondly, since we haven't invented a brand new fuel to replace fossil fuels, it appears that today, with the currently known technologies, what we need to do is to deploy a combination of these technologies to decarbonize many different forms of clean energy. So that decarbonized future will comprise of many different things, as you mentioned, biofuels and green hydrogen, etc. So we create scenarios of what the future energy system might look like, but there's a huge range of uncertainty. And of course, the oil and gas companies are formulating strategies to deploy shareholder capital in this without destroying that capital. So the strategies need to be pragmatic. And so firstly, when it comes to Scope 1 and 2, they are already, I think, deploying measures that should help reduce those. So they're working very actively to stop methane emissions, to stop routine flaring of the gas, to electrify all their utilities by renewable sources, to switch from grey to blue and green hydrogen, CCUS, etc., etc.
So assuming we get a harsher regulation, do you think energy companies might disappear in 2050? Or are we likely to see a more bipolar world, one fully powered by renewable and the other one still dependent on fossil fuel? For example, developed markets or developed economies versus emerging economies?
I personally believe that some, if not all, of today's oil and gas and energy companies will be with us by 2050. And the reason I say that is I just look at the IEA's 2050 net zero scenario, which is used for consensus. And this shows that for the world to decarbonize, we need to grow materially electrification through renewables. When I say materially, from 20% currently to 50%. But if you then look at the other 50% of that decarbonized future, it comprises of decarbonized liquids and gases like biofuels, sustainable fuels, e-fuels, renewable natural gas, blue and green hydrogen. And so essentially what it says is that renewables electrification is only half of the story by 2050. The other half is very much the area where the oil and gas companies have their assets and where they and their customers are working to decarbonize hard-to-abate sectors like airlines, shipping, heavy-duty transport, heavy industry, the current fossil fuel consumer who by 2050 will be using decarbonized fuels, and today's supplier of oil and gas will be the future provider of those decarbonized liquids and gases, which is the 50% outside renewable electrification. So today's fossil refineries using fossil hydrogen become the biorefineries using green hydrogen of 2050. And one other key dimension, of course, is the financial one, why I think they will continue to exist. Clearly, a brownfield refinery conversion from fossil fuels into biorefinery costs today a very small fraction of building a new greenfield biorefinery from scratch, which is what a newcomer would have to do. So I think the oil companies can convert to wider energy companies and potentially can do so at a lower cost than the newcomers.
Indeed.
And that is why I'm an optimist.
Excellent. So last question for you. We are going to run out of oil and fossil fuel at some point. When is that and what happens then?
So according to the IEA, peak oil demand should happen by 2028 and peak natural gas demand, even in their least aggressive scenario, should happen by 2030 at the latest. Having said that, other forecasters disagree. So, frankly, no one quite knows. And what we observe post-pandemic are pretty normal oil and gas demand patterns. I think there's two relevant points here. The first one on natural gas. Natural gas in the emerging market world can emerge as a key fossil fuel. It can help emerging countries switch from coal-fired electricity currently to gas-fired, and in the process reduce 50% their emissions. So, I wouldn't be that confident that gas in particular would just peak over the next decade. And the second point is that it is perfectly feasible that even by 2050, we will still be consuming oil and gas. Because remember, global society goal is net zero by 2050. It is not absolute zero. Net zero means carbon neutrality, not elimination. And carbon neutrality means we reach a balance between possibly continuing to emit carbon from some oil and gas production, but absorbing that carbon from the atmosphere in carbon sinks. So I think the precise date is unknown.
Indeed. And I think your point around carbon neutrality is a key one, hence the importance to maintain and protect the carbon sink, which is essentially biodiversity, forests, and also develop carbon capture and storage in a more efficient and economic way. This was fascinating and very insightful, Irene. Thanks so much for your time, and looking forward to carrying on the conversation at some point.
Thank you for having me, Kokou. Thank you.
The main reasons animals feared the red flower in the Jungle Book is obviously because of its destructive power. It has and continues to destroy their natural habitat, forests. I will conclude this episode with the story of the hummingbird, as told by Professor Wangari Maathai, a Kenyan environmental and political activist, Nobel laureate, and writer. The story of the hummingbird is about these huge forests being consumed by a fire. All the animals in the forests come out and they are transfixed as they watch the fire burning. And they feel very overwhelmed, very powerless, except this little hummingbird. It says, "I'm going to do something about the fire." So it flies to the nearest stream and takes a drop of water. It puts it on the fire and goes up and down up and down as fast as it can. In the meantime, all the other animals, much bigger animals, like the elephant with a big trunk that could bring much more water, are standing there helpless. And they are saying to the hummingbird, "What do you think you can do? You are too little. This fire is too big. Your wings are too little, and your beak is so small that you can only bring a small drop of water at a time." But as they continue to discourage it, it turns to them without wasting any time, and it tells them, "I am doing the best I can." Thank you for listening to this episode of 2050 Investors. And thanks to Irene Himona for her time and valuable insights. I hope this episode has helped you get a better sense of the future of energy. You can find the show on your regular streaming apps. Please subscribe, leave comments and stars anywhere you like, and spread the word. See you at the next episode. While the following podcast discusses the financial markets, it does not recommend any particular investment decision. If you are unsure of the merits of any investment decision, please seek professional advice.